Hi folks. Last time we finished up our talk about sensors, and so after sensors we want to talk about actuators. But just like before, we're going to chunk this up into a couple of videos. We'll start with talking about types of actuators and DC motors, and then we'll move to stepper motors. So first things first, why do we care about sensors and actuators? Well, we hit on this when we talked about sensors already. If we have a real-world system that we want to interface with, whether it's our project or something else, and we have our state machine that is on the microcontroller, then certainly we need some way to understand what's going on in the real world, that's our sensors, and then use our state machine to control what's going on in the real world, that's our actuator. So we want to be able to interface our real world system with our digital controller, and again, this is a supervisory level controller, not necessarily a part level controller in this particular class. So in terms of types of actuators, I would have a discussion prompt at this point in a regular class where I would ask you to think about the types of actuators that you need in your particular project for the semester, and what are you thinking about in terms of initial design, and how does that relate to the choices, and then we'd go around the class and see what everybody had so that you could get an idea of all the different actuator modalities that people already know about and are already thinking about for their projects. But we're not in a regular class, and so I'm just going to skip this prompt. So I encourage you to pause the video right now and write out for yourself a list of the different actuators that you might use for your project. And we're moving on. So one of the actuators that we always come back to is a DC motor. And the reason we do DC motors is that they are a really nice way to control speed or position. They are simple to use, they're well known, they're great. We're going to use them in lab. We're going to talk about them in the rest of this video. Great, simple, easy to use. One of the things that people often will try to use then is a step from a DC motor to a servo motor. So what is the difference between a DC motor and a servo motor? Well, a DC motor, you apply a voltage and it spins, which is to say that you are applying a voltage and getting speed, versus a servo motor, you are applying you're applying a supply voltage in terms of power, but you're applying some sort of signal and you're getting position. So the idea of a servo motor is just that it's a DC motor with control added to it. So you get feedback control often in form of simple PID controller, and so you are controlling position. Now, when we buy these, often we buy hobby servo motors that are originally intended for things like RC vehicles, be they cars or planes or whatever. And so internally they have a gear head and they have the controller built in. And so they come in different sizes and different costs and different torques and all sorts of different varieties. So often the way that these will run is that there will be an angle that you are specifying, and it'll be specified by the duration of a pulse. And so this is not PWM. This is the time duration of a pulse. Why does it go that way? I have no idea, really. But that is the standard that I have seen. So a 1.5 millisecond pulse will go to a neutral position, and then if you go to shorter, it'll go one direction. You go longer, it'll go the other direction. So maybe 1 millisecond to min and 2 milliseconds to max. So again, this is not PWM, but it is a known standard that we can use. And there is a limit in terms of torque. So the example that I always use here, and this works better if you can see me in person waving my hands around, but that I saw a student many years ago that designed a gate for his robot, and this gate was to open and allow a tennis ball to go in and then close. And so the student placed a servo motor on the gate and specified that the gate should rotate 90 degrees to open and then rotate 90 degrees the other way to close. Works pretty well. So rotate 90 degrees, drive forwards to pick up the tennis ball, rotate 90 degrees the other way, close, tennis ball is captured. Except that this student chose to put two gates on and had to operate gate A and then B in the right sequence to open gate and then A and then gate B, and they were one in front of the other. So these things have a torque rating. Well, what happens when you open gate B and then A? You had a clash, and the torque was such that it stripped the teeth right off all the plastic gears and then ruined a servo motor. So when you're using servo motors, you got to be a little careful about these torque ratings, and the limiting factor is usually the plastic gears or the metal gears, and obviously you're going to pay more for the metal gears. So be a little careful in terms of using servo motors to make sure that you're using them appropriately. Also, nitpicky sort of personal complaint is that when I think about servo motors, I think of somebody having done the controller design for you already. So remember, they are position control, not speed control. So you get whatever response characteristics the designer chose. If you want a particular response rate, you got to buy one that has that response rate. If you need a particular response rate and it's not available, you're going to have to design your own servo motor. But fortunately, we go over how to do that in mechatronic systems too. So in terms of analog and digital, there are different speeds here. There's different characteristics. Again, you got to choose the one that's appropriate for you. Servo motors are not always the right answer, but they are frequently a good answer for position control tasks. Other types of actuators you're going to run into, well, we could have solenoids and relays. These are good ways in order to control linear motion and flow of current, and these are based on electromechanical principles. Piezoelectric is something that I've dealt with quite a bit. Piezoelectric materials are going to respond to a charge. Will apply a voltage usually, but they are going to expand or contract in the presence of a charge. That's the actuator side. Certainly remember, a piezoelectric material could also be used as sensor, where it is going to turn a compression or an expansion into a charge which is measurable. So in the actuation side, you're going to apply this voltage and then you're going to get motion. So on the middle, the left there, we'll start with the left, you can see that there are these discs of material that are all stacked up, and because they're polarized, they all have a preferred direction. And you notice that they are all powered between, from top to bottom of one of the cylinders, and so they're all flipped in terms of direction. So when you apply a voltage here, you're going to energize each of these, and they're all going to expand. And because of the way the plates are stacked in terms of the electrode stacks, they are all electrically in parallel, but they're mechanically in series. And so when they all expand mechanically in series, you get a total expansion that is significantly larger than the expansion of any one of the disks. You still only get something like 1% expansion, but it's not terrible when you talk about a bunch of disks stacked up like that. So you can see an example of in the middle of one of these stacks, and they don't all look exactly like the one on the left, but the stack there in the middle also has these little flexure hinges. So let me make sure my pen is working. So here is our stack, and then these little things are flexure hinges. There goes my pen again. Flexure hinge. And these hinges are made by removing material. So you cut away enough to leave a little bit of material there, and then it bends about that material like it would about a hinge. So it is a nice way to machine a hinge into something. So in this case, you fire up your stack with a voltage. The stack expands, and then the use of those hinges gives you essentially a lever to get a larger expansion on the entire device. You can also see some flat pieces here. These flat pieces are great for creating curvature or vibration. Again, you have to be careful with piezoelectric material because one of the things they also can do is generate heat. And I saw a great example of this with a plate like this, that a student was looking to control the curvature of a helicopter blade by actuating the piezoelectric material. And so when they did that, they unfortunately were vibrating it very quickly and not thinking about the heat, and it was sitting flat on a table, and it went into a runaway heating and burst into flames. So you got to be a little careful about runaway heating on these things. All right, I love piezoelectric materials. We can talk about that all day. Other examples of actuators, valves. You can use valves to actuate things. You can talk about having hydraulic or pneumatic actuation. We could certainly do that in the lab. You can see an example on the right of a valve that's driven by electromechanical action. You could also talk about combustion type actuators, so an internal combustion engine, turbine engine. These are great examples of much larger actuators. Not the sort of thing we're going to do in lab, unfortunately. So, now that we've talked about those, the thing that we're going to focus on in this class is going to be a DC motor. Again, it's a small, frequently used device that is very well known and works well for a lot of our robots. So we're going to start in this video by talking about DC motor design, and then we'll talk about operation in the next video, and then we can go stepper motors in the following video. So DC motors start way back in 1821. So Faraday showed that if you've got a current running through a wire, there's a magnetic field around it. So on the left of this particular one, this one is Faraday's experiment, if I can spell it correctly. So there's Faraday's experiment. And then building on that, Henry built this rocking actuator. And so it rocks back and forth by making contact on these batteries, essentially. And certainly that one can just rock back and forth. But if you want rotary motion, now you need to have a commutator. And so Sturgeon here has a commutator, a real simple one. You can see that this is the like most basic commutator you can have, and it doesn't work as well as what we have now, but this is a very simple commutator. Oh, and if you don't remember what a commutator is, or you haven't heard that term before, that's the thing that is switching the direction of the current, and so you'll see that shortly. So the general principle of all these is the same. If you apply a higher voltage, you get a higher speed out. If you reverse the voltage, you reverse the speed. So you can go either direction, which is great. So now we need to have a way to control the voltage applied to the motor and reverse the direction of the voltage, which means that we need some sort of control. And we'll get to that. We'll get to that with H-bridges. So we've got this armature circuit and we've got this field. So the field is generating some sort of magnetic field, and it could be from a permanent magnet or it could be from a coil that is fixed, but either way it's generating a field. And then we've got this armature circuit, and the armature is a winding of wire. And so a long winding of wire, we know because it's winding it's going to have an inductance, and because it's relatively long we're going to have some resistance. So the resistance should be small, but it should still be there. And we're going to apply a voltage. So when we think about the physical dimensions of this, we have to include that R and the L in there, and it makes a circuit, so we got the current going through it. And so as the current goes through the circuit, we are going to then generate torque. And then as this thing moves through the electric field, we're going to generate a back EMF. So the back EMF is represented here, and the torque is shown as moving the rotor. So we can do this two different ways. We can control the voltage on the armature circuit, and that'll control our velocity, or we can control the current through it, and that'll control our torque, because the torque is going to be proportional to the current. So two different ways to do it. I think in this class we're going to do almost exclusively voltage, but certainly current control is not impossible. It just requires a little bit more circuitry. So this is an example of a really cheap motor. You can see this one was only about $3 at the time that this image was taken. This one has all the basic things that you would expect to see. We've got some contacts on the back here. We've got a stator. That's the stationary part, the part on the outside that doesn't move. And we've got the rotor, and that's the part inside that's spinning. So as you apply a voltage to the contacts and hold the stator still, the rotor turns. Notice that these are, again, really cheap. One of the problems you run into here is that the contacts can tear out easily. It's probably not going to generate a lot in the way of torque, but it's got all the major features. So as I said, the rotor is the part that is rotating. The stator is the part that is stationary. The field system, that's what's generating the magnetic part. So again, it could be coming from a permanent magnet, or it could be coming from an electromagnet. It could be either way, just as long as it's generating a field. The armature, this is the part that is going to be carrying the current, and then the brushes is going to be where the circuit is made between the outside and the inside, basically. So that's between the contacts and the through the commutator to the armature, and then the commutator is this thing that's back, and so as you're rotating the rotor, the commutator is in contact with the brushes, and it's switching the direction of the current. Okay, so here is a couple of rotor examples extracted from different motors. You can see that there are different patterns in terms of the winding of all these wires. So this one is called lap winding. Lap winding, there we go. And this one here is called wave winding. And so you can see the text here. So the wave winding, look at this one here, we've got two current paths, and the lap winding, we've got however many paths is how many poles we've got. And so there are different characteristics here. Do you want high current, low voltage, or high voltage, low current? Kind of depends which one you're going to get. So two different winding schemes. Now, are you going to specify a motor based on lap or wave winding? No, you're going to specify a motor based on the speed and the torque, and then it's going to be an option of what somebody has built to meet that. So the stator then has the magnets. So this is a good example of permanent magnets. Again, this is a relatively cheap one, but this has the permanent magnets built in. You could get a fancier one with more magnets. You could get a fancier one that's got the electromagnet. The ones that we use in class are going to be on the cheaper end. And then here's a nice picture of the brushes and the commutator. So we've got the brush there. It's a chunk of carbon there that's going to allow you to have a contact. And the commutator, you can see the winding pattern there. You can see it's got all these different contact points that are making contact between the commutator and the brush out to the contacts on the outside. Now notice what happens is we've got this brush that's rubbing against the commutator as the commutator is spinning. Well, of course there's going to be friction, and so of course the brush is going to wear down. So in a expensive motor, like the picture, the larger picture here, eventually the brush is going to wear out and you'll replace it. You'll put in a new brush and you'll be able to clean out the dust that comes from it and you'll be fine. Versus the cheap one in the upper right, you can see that those brushes are going to eventually fail and you'll have to replace the entire motor. You cannot replace just those brushes. I had an example in lab of a student had applied too high a current, I think. I found it after the fact, so I'm not sure exactly what they did, but I think they applied too high a current and they melted that housing on the back, and so the brushes were no longer in good alignment and were not connecting to the commutator, and the motor is ruined. Fancier, more expensive motors, less of a problem with that. You can see that there's alignment guides here. You can see that the brush is held nicely in place. You can even see a spring to make sure that the contact force is nice between the brush and the commutator. So a lot of differences in terms of motor construction. You do get what you pay for. Oh, and since the brush can wear out, the brush is the failure mechanism for motors. This is where you're going to see most of the failures, and you're also going to see some noise from the contact being intermittent. So the commutator is a switch that's redirecting the current. So as the brush is contacting this and as the commutator is turning, it is redirecting current back and forth, because that's going to allow for the torque to be even. And we'll cover, don't worry, we'll cover that as we get to the operation part that's next. So it's going to change which circuits are going to have the current. So again, here's a nice picture of a cheap one. You can see that this one has relatively few contact spots, and it's got brushes that are just bent pieces of metal here, and so you would expect that to be a failure point. Okay, so that is basic pictures of the construction. I'm going to stop the video here, and then the next video is going to pick up with operation.